All right, so last time we did take a look at when we violate our assumptions, how bad it can get. I skipped over some of these tables. We'll cover some of them in class. Some of these, it's interesting, but not essential. It's really just making the overall point that we do need to pay attention to these assumptions, normality not being the foremost among them. Again, heterogeneity and dependency to me being the biggest factors. If we have dependent data, like I said last time, we need to go use a whole entirely different class of models. Heterogeneity we can often do a lot about, and we will see what that is like in class. All this should make you wonder, as Gary says, about people who obsess over whether the p-value is 0.051 or 0.049. Long ago, I quit even worrying about 0.055 versus 0.045. Little violations of your model can cause that kind of change in the p-value. And as we talked about in class 2, really, if we interpret the p-value correctly and not as a radical binary decision, there's substantively no difference between those two values anyway. Residuals. So on to residuals. Remember that the residual is just the observation minus the fitted value. Okay, because this is just a linear model, we need to be paying attention to these residuals. So the basic raw model, raw residual is, as I said, fitted this way. How would we find that fitted value? Well, it's our estimated grand mean plus the effect estimator. So that's really just the difference between the treatment mean and the observed value. Okay, because we're just saying if the, say, a one-way CRD ANOVA model fits, then we're just saying every one of these YIJs is just estimated by YI bar dot. The residual is useful to assess lots of things, including the normality. We can assess it that way. But the standardized residual is often useful for picking out outliers. So the standardized residual, sometimes called internally studentized residual, just adjusts the residual, the estimated residual, using its estimated standard deviation, which is MSE 1 minus this value from what we call the hat matrix. When I teach regression analysis, we do a lot of work into understanding this hat matrix. I'm not going to do that in this class. You can see the hat values in R using this command. These should more or less look like standard normal random variables. If we have a large enough sample size, they really should. If it's kind of a smaller sample size and we have a little bit of heavy tailness or something, I just don't worry about it. And those numbers from the past lecture makes clear why we shouldn't worry about that. The studentized residual, this is not internally studentized but externally studentized, is the following. We take the degree of freedom for the mean squared residual and do this little transformation of it. If this model is correct, this should be a t-distribution with v minus or nu minus 1 degrees of freedom. If you recall, once nu, the degrees of freedom for the error get kind of large, like 20 or more, this should look really like a normal, more or less. These are really good for looking at outliers, looking for outliers, I guess. Gary kind of gives you a conceptual understanding about what this studentized residual is doing, and it's really looking at how much of a model-based outlier each observation point. So you can add a dummy variable to your model, and that t-test for that dummy variable is going to be your studentized residual for that point. So it's seeing how much that point deviates from the whole model. So we're not saying it's a deviation with respect to y or with respect to x, but with respect to the entire model instead. I'm with Gary on this. Numerical tests for normality and constant variance kind of drive me nuts, to tell you the truth. I'm not in favor of them. They get inappropriately picky much of the time, and in other weird cases aren't picky enough. I just do not like them. Plus, I don't think it develops good intuition like looking at plots and doing good exploratory data analysis does. So with small sample sizes, you're never going to be able to reject your null hypothesis that there are no problems. And with large sample sizes, you're constantly going to be finding non-normality when in fact it doesn't matter. So it feels like in both cases, these tests for non-constant variance and normality just tend to confuse things instead of clarify things. And I have gosh, maybe I'll dig out for class. From another class I used to teach, I wrote up a whole handout that we did in class. I'll bring it at least, called Why I Don't Use Normality Tests, and it illustrates this about how problematic and how misleading they can be in terms of being not picky enough or overly picky. I just don't care for them. And I like a qualitative assessment of assumptions because I hardly ever feel like I'm getting led astray if I use it that way. Okay, so we're going to focus on qualitative methods here. So we're going to use the following to qualitatively assess whether or not our assumptions are met using the residuals. A normal probability plot of your residuals. We'll take a look at this in class also here. Residuals versus predicted plot. This one's a very standard one we use in regression analysis as well as here. And the residuals in time order just so we can rule out dependence. These first two I'm sure you've seen before, and the last one we do in regression modeling too. So I think this is pretty consistent with stuff you've probably done. The normal probability plot, I'm going to skip over this. I don't really want to spend time on this. You probably get this in other classes anyway. I think we're all familiar. We can use the studentized residuals for this. I think it's fine to use any kind of residual personally, but Gary recommends the studentized, so I think that's usually what I use anyway. So normally distributed data should have a roughly linear shape to it, even though we have underlying normal data. Sometimes at small samples it'll look kind of crooked, so we need to develop an intuition about what's a violation and what's not here. You can tell the shape of your data from the shape of the plot. I do have a handout that I'll bring that kind of gives you rules of thumb for that. Okay, so here's some data, the QQ plots. Notice none of these are linear. If this were normally distributed data, we'd just see a line straight across here that would be very diagonal and not deviate from that diagonal. Okay, so we see long tails here, so we see a big dip on this end. It kind of starts lining up and then dips down. Here we see the dip on the lower end for short tails. Okay, so that's your first kind of clue. Maybe a little bit above the line here. You really don't see it here partially, just there's some smaller sample size perhaps, or it's real clustered, that data. You can also see where most of your data is by the density of the plotting points as well. Skewed right, so skewed right, notice it's below the line. Skewed left, it's above. So pretty nice rules of thumb. I actually probably won't bring my handout because this is basically all my handout shows is this. So you could print this out and label it. Write notes to yourself, and this is a nice way to start developing your intuition. So IAD normal, notice we do see random scattering, so don't get worried about minor deviations. That looks good to me. That's also IID normal. We have small sample size. You don't need to be so picky. Notice it does go below the line a little bit, so you might be going, does it look like it has long tails? No. Look how small the deviation is. This is also IID normal. Okay, we have two kind of weird points down here. And then there's maybe something going on or starting to go on here, but it's not egregious enough to say we've really deviated from a normal distribution. Likewise here. So this is a cautionary tale. Don't get too picky, especially these are all small sample size settings. You can use the studentized residuals to also test for outliers. I think that's a nice idea to just plot them like in a box plot and see how many deviate from outside the interquartile range area. I would not be add that to your list of things to do. That would not hurt. The diagnostic plot for non-constant variance is basically the residual against fitted plot. We want to see just what I like to call a cloud of points. So no particular pattern or shape. We don't see a curve to it. It's just a cloud of points with no shape. What we most often see is that the larger means go with larger variances. That's common with a lot of statistical distributions, think Poisson or something. And in those cases, we do see a right opening megaphone. So that is like the most popular shape you'll see with heterogeneity indicating plots here. Sometimes you'll see a left opening megaphone if you've got some truncation or something in the data. There are other, I've seen also a double-ended megaphone where I saw the extremes of the data having large amounts of heterogeneity, and then as you got closer and closer to the mean of the data, it calmed down a lot. So it was like two megaphones where the mouthpiece part was butted up against each other. If you want to make a test for equality of variances, your best bet is Levene's, but again, like I said, I just don't care for these tests, and I would much prefer to see a plot on your homework. I think, again, these are going to tell you much of the time you have problems with variance, especially when you have a small sample size, when you really don't need to worry about it. But to make yourself feel better, go ahead and do it if you like. There's a lot of variations on this and other things. These ones, I didn't really know this, but Gary points out these two, which are some older tests, are really hypersensitive to normality. So just don't use them, or to non-normality, that should say. So back to the resin example. Let's do that in class, I'm thinking. So we'll go in detail into this resin example and another one in class. I have two written up if I recall, and we'll stop there.